We will start the session at 6 p.m. Okay, good evening and welcome to the problem solving session for week 12 for the NPTEL course Heat Transfer with course ID noc24-ch17. My name is Nidishji and I will be your teaching assistant for today. Okay, these are the week 12 topics. This will be, I think, the last week for this course, and for this week we had 5 lectures, all focused on the heat exchangers, heat transfer through heat exchangers. The first lecture for the week, that was lecture 56, talked about introduction and examples of heat exchangers. The concept and importance of heat exchangers was discussed in detail in this lecture, and various configurations for heat exchangers along with the utilities were presented, like parallel flow, cross flow, shell and tube heat exchanger, and so on. In the subsequent lecture 17, concept of universal heat transport coefficient was as applicable to the heat exchangers was discussed, and the parallel flow heat exchanger was also discussed. In lecture 58, which focused on LMTD, that was log mean temperature difference, the parallel flow heat exchanger was modeled and a method to systematically design this heat exchanger was described. Co-current and counter-current operation modes of heat exchangers was also presented in this lecture. In the next lecture, that was lecture 59, the shell and tube heat exchanger was discussed. Example problems involving heat exchanger design was solved, and shell and tube heat exchanger design was also discussed in this lecture. In the subsequent lecture, that was lecture 60, the effectiveness NTU method was discussed, which was used for systematically designing heat exchangers, and these effectiveness NTU relationships for different cases were summarized. These 5 lectures were talking about heat exchangers in particular, and that was the last topic for this course. So with that we will begin our problem solving session for today, and it is expected that before attending this session everyone has gone through these 5 lectures and understood the concepts of heat exchangers. Okay, with that we'll begin our problem solving session for today. Okay, here is the first problem for today. Let me read out the problem statement for you. Consider a concentric tube heat exchanger characterized by a uniform overall heat transfer coefficient and operating under the following conditions. Okay, we have a concentric tube heat exchanger with the conditions as given in this diagram. We can see that the inlet temperature of the hot fluid is 210 degrees Celsius and inlet temperature of the cold fluid is 40 degrees Celsius. Also, the outlet temperature of hot fluid is not given, and the outlet temperature of cold fluid is given to be 95 degrees Celsius. Simply by looking at this temperature profile, we can say that it is a parallel flow heat exchanger. And let's look at the remaining part of the question. Mass flow rate of the hot and cold fluid is 0.125 kilograms per second. If a counterflow heat exchanger is operated under the same situation, what is the ratio of the required areas for these two flow conditions? That is, we need to find the area of counterflow heat exchanger divided by area of parallel flow heat exchanger. We need to find this ratio. Again, some more information is given to us. The heat capacity for the cold fluid is given to be 4200 joules per kilogram Kelvin, and the heat capacity for the hot fluid is given to be 2100 joules per kilogram Kelvin. We have this much information. So take a minute to go through the problem, and after that we will discuss the problem as well as the solution. Okay, I think the problem statement should be clear. We have been given the inlet temperature for the hot and cold fluid and the outlet temperature of cold fluid for a parallel flow heat exchanger, and the mass flow rate for the hot and cold fluid both are given to be the same as 0.125 kg per second. And now it is given that we have to design a counterflow heat exchanger which would be operating under same situation, means total heat transfer rate would be the same. So for that scenario we need to find out the ratio of these areas, corresponding areas available for heat transfer in this counterflow and parallel flow heat exchanger. So how can we proceed that? Think about that for a moment. By that time let me redraw this graph here. Okay, what we need to find out is area available for heat transfer for the counterflow heat exchanger divided by area available for heat transfer for the parallel flow heat exchanger. This is what we need to find out. Okay, now can we relate this to our total heat transfer rate? We know that the heat transfer rate for heat exchangers, either parallel flow or counterflow, can be given by the product of overall heat transfer coefficient into multiplied by the area into product of into the log mean temperature difference, delta T LM, U A delta T, similar to H A delta T. It is given by, instead of H, here it would be an overall heat transfer coefficient for the heat exchangers. This is the expression that we have. From this we can write the area, rewrite the area available for heat transfer as Q divided by U into log mean temperature difference. Okay, so if we substitute for this value in this expression that we need to find out, we can rewrite this expression as area of cross section of counterflow heat exchanger divided by area of cross section of parallel flow heat exchanger equal to area of cross section is Q by U into delta T log mean temperature difference. The Q for counterflow heat exchanger divided by U in terms of counterflow heat exchanger and delta T LM for counterflow heat exchanger divided by Q parallel flow heat exchanger divided by overall heat transfer coefficient for parallel flow heat exchanger into delta T log mean temperature difference for parallel flow heat exchanger. Is it clear up to this point? If so, we can further simplify this expression actually. We can further simplify this expression. we know that these two heat exchangers are supposed to operate at the same conditions. If I go back here, if a counterflow heat exchanger is operated under the same situation, that means that this Q and U should be same. Q counterflow should be equal to Q parallel flow, and U counterflow should be equal to U parallel flow. When these two heat exchangers are supposed to be operating under same conditions, this is what that means. So these expressions, this Q and U would get cancelled from numerator and denominator, and this would simply be turn out to be a ratio of the log mean temperature difference of parallel flow heat exchanger divided by log mean temperature difference of cross flow heat exchanger. Okay. Is that clear? Now the problem reduces to finding ratio of this log mean temperature difference. Say I'm calling this as 0.1 at the inlet and 0.2 at the outlet. Then how can we define the log mean temperature difference? Log mean temperature difference is equal to the temperature difference at the section 1 minus temperature difference at the section 2 divided by log of ratio of temperature difference at section 1 divided by temperature difference at section 2, right? Let's see if we have these quantities for all the cases. For the parallel flow heat exchanger, this is parallel flow. For the parallel flow heat exchanger, we can see that we don't know the outlet temperature of hot fluid. This temperature value is not yet known. So how can we calculate that temperature? Any thoughts on that? We can equate the total heat transfer heat that is absorbed by the total heat that is lost by the cold fluid is equal to the heat that is gained by the hot fluid, right? We can use that concept here. So I will rewrite it as M into temperature of specific heat of hot fluid into temperature difference of hot fluid, T hot at inlet minus T hot at outlet is equal to mass flow rate into specific heat of cold fluid into temperature of cold fluid at the outlet minus temperature of cold fluid at the inlet, right? Among these, the mass flow rates are given to be the same, so I will cancel them out. Now the quantity that is unknown is TCO. So I can write it to be equal to TCI plus C hot by Cc into T hot inlet minus T hot outlet. This is what is the expression for finding out temperature of cold fluid at the outlet. Temperature of cold fluid at the outlet is known to us, right? What we have to find out is temperature of hot fluid at the outlet. It is THO that is unknown to us. So I can write temperature of hot fluid at the outlet equal to if you rearrange these terms, this would be temperature of hot fluid at the inlet minus C by CH TCO minus TCI. This is the expression for temperature of hot fluid at the outlet. And let us substitute these values and get the expression. What are Cc and Ch? 4200 joules per kilogram Kelvin and 2100. So Cc by Ch would be 2. So this is equal to temperature of hot fluid at the inlet is 210 let us calculate that value. Okay, so once we evaluate, we will get it to be 100 degrees Celsius. This is the unknown temperature of hot fluid at the outlet. So let's now write delta T log mean temperature difference for parallel flow heat exchanger equal to, again the previous expression was delta T1 minus delta T2 by logarithm of delta T1 by delta T2. This is 210, this is 95 and this is 40. So this becomes equal to 210 minus 40, that is 170, minus 100 minus 95, that is 5, divided by ln of 170 by 5. Let's evaluate that expression. Oops, sorry. Let's evaluate that expression. (170 minus 5) divided by ln of 170 by 5. 46.79 or 46.8. Yeah, we are getting a value of 46.79. Similarly, can we get the expression for delta TLM log mean temperature difference for the counterflow heat exchanger? What would be the difference? This was parallel flow and now we need counterflow. Counterflow, let the hot fluid be like that only. At inlet it is having 210 degrees Celsius and outlet it is having 100 degrees Celsius. And the counterflow heat exchanger, it is coming from here, right? So at inlet it is having 45 degrees Celsius. This is the direction of flow from here to here, and for the counterflow heat exchanger it would be like this. It was initially at a temperature of 40 degrees Celsius and it would come to a temperature of 95 degrees Celsius in the counterflow direction. So when we write delta T1 minus delta T2, delta T1 minus delta T2, in all the cases 1 and 2 I am taking this to be this section and 2 I am taking to be this section. Okay. Sorry. So it would be equal to delta T1 would be 210 minus 95, that is 100, 110, 115 minus 60 divided by ln 115 by 60. Let us evaluate this expression also. Minus 60 divided by ln 115 by 60, 84.53. So the answer I am getting is 84.53 or 84.54. 84.54, yes, that is what I am getting. Is it clear up to this point? So if it is clear, the required ratio of areas turns out to be area available for counterflow divided by area available for parallel flow we have already found out that this is the ratio of log mean temperature difference of parallel flow to the log mean temperature difference of counterflow. Log mean temperature difference of parallel flow divided by log mean temperature difference of counterflow, which is equal to 46.79 84.54, which is equal to about this is the final answer. Sorry, this would be the final answer. Take some time to go through the problem and solution again and let me know if there was something that was not clear. Let me go back to the problem statement. Let me go to the solution. We wanted to first find out the ratio of available area for heat transfer for counterflow and parallel flow heat exchanger. So area we wrote in terms of Q, U and log mean temperature difference, and Q and U turned out to be the same in these cases, and the equation reduced to just a ratio of log mean temperature differences. For log mean temperature difference, we needed to find out the temperature of outlet temperature of the hot fluid, that we found out using an energy balance. And for the parallel flow and counterflow heat exchanger, we drew the temperature profiles and we found out the log mean temperature difference. We found out the ratio to get the ratio of area for heat transfer in counterflow and parallel flow heat exchanger. Is that clear? I will give a minute to go through the solution. Okay, let's move on to problem 2. Okay, I hope problem 1 was clear, right? There was no confusion. Okay, if so, I will move on to problem 2. Let me read out the problem statement. A two fluid heat exchanger has inlet and outlet temperatures of 65 degrees Celsius and 40 degrees Celsius for the hot fluid, and 15 degrees Celsius and 30 degrees Celsius for the cold fluid. Okay, let's try to draw this. Let this be some inner tube. Say this is hot fluid. Say this is cold. Okay, inlet and outlet temperature of hot fluid are 65 and 40. 65 degrees Celsius, 40 degrees Celsius, and cold fluid inlet is 15 degrees Celsius and outlet is 30 degrees Celsius. Cold fluid is getting heated, or the hot fluid is getting cooled down. Determine the effectiveness of the heat exchanger. Effectiveness epsilon of the heat exchanger. Consider C min equal to C hot. So it is given to us that C min, that is the minimum heat capacity, is equal to be taken as the heat capacity of the hot fluid. First, C stands for MCP. Yeah, C stands for MCP. Okay, this is the problem statement. Take a minute to go through the problem statement, and after that we will proceed to solve this problem. Okay, shall we proceed to solve this problem? Take one more minute, and after that we will proceed to solve this problem. Okay, we are given hot fluid and cold fluid, inlet and outlet temperatures, and we need to find out the effectiveness. So what is the expression for effectiveness of a heat exchanger? Effectiveness can be defined as the ratio of heat transfer rate of either the hot or cold fluid by the maximum possible heat transfer rate, right? So the maximum possible heat transfer rate is defined as the product of minimum heat capacity into the temperature of hot fluid at the inlet minus temperature of hot fluid, sorry, temperature of cold fluid at the inlet, right? This is the definition for Qmax. Since we have been given that C min equal to C of hot fluid, we can write the denominator in terms of hot fluid so that this C and C get cancelled. Because we don't know the value of C yet, we only know that C min equal to C max, C min equal to C hot. So if you write Q, that is the total heat transfer in terms of the hot fluid, it will be temperature of hot fluid at the inlet minus temperature of hot fluid at the outlet. Is this expression clear? If so, we can directly substitute the given values in this expression and find out the results. This C hot and C min were given to be equal in the problem, and effectiveness reduces to T hot inlet minus T hot outlet, that is temperature of the hot inlet minus temperature of the hot outlet, 65 minus 40 degrees Celsius divided by T hot inlet minus T cold inlet, 65 minus 15. This would be 25 by 50. This would be 0.5. So this means that the effectiveness of the heat exchanger that is given to us is 0.5. That this heat exchanger can achieve 0.5 times the maximum possible heat transfer rate for the given inlet conditions for hot and cold fluid. Okay, so take a minute to go through the solution, and after that, this was a small problem. We had to find out the effectiveness of the heat exchanger, and we know that it is the ratio of heat transfer rate of either the hot or cold fluid divided by the maximum possible heat transfer rate. With that, we substituted all the values and found out the solution. Problem 1 and problem 2 slides once, please. Okay. This is problem 1. This is problem 2. Thank you. So I think problem 2 was also clear. So we will move on to the third problem. Okay. Okay. Here is the third problem for today. Let me read out the problem statement. Saturated steam at 0.114 bar is condensed in a shell and tube heat exchanger with one shell pass and two tube passes consisting of 130 brass tubes, each with a length per pass of 2 meters. The tubes have inner and outer diameters of 13.4 millimeters and 15.9 millimeters respectively. Cooling water enters the tubes at 20 degrees Celsius with a mean velocity of 1.25 meters per second. The heat transfer coefficient for condensation on the outer surface of the tubes is 13,500 watts per meter square Kelvin. Determine the overall heat transfer coefficient. And we have been given properties of steam and water and brass. Take a minute to read the first paragraph, that is the problem statement, and after that we will discuss the problem as well as the solution. We need to determine the overall heat transfer coefficient in this case. Okay, it's a shell and tube heat exchanger with saturated steam going through the shell inlet and which is condensing by means of a cooling water which is coming through tube pass tubes with each pass of length 2 meters. 130 such brass tubes are available with given inner and outer diameters. The temperature at the inlet of the tubes, temperature of cooling water at the inlet of tubes is given to be 20 degrees Celsius and the velocity is also given. Also the heat transfer rate associated with condensation on the surface of the tubes, that is the outer surface of the tubes, is also given. And we have to determine the overall heat transfer coefficient, U. All the properties that we would need are also given to us. Okay, let me proceed to solve this problem. Is the problem statement clear? Yes. So let me define the overall heat transfer coefficient with respect to the outer surface area of the tube. There is shell and tube, right? So let me define the heat transfer coefficient with the outer surface area of the tube. Let A0 be the outer surface area and AI be the inner surface area. So it can be written as, now what all are there? There is a heat transfer rate associated with the inner surface, not heat transfer rate, heat transfer coefficient. There is a heat transfer coefficient associated with the outer surface, and there is a resistance also associated with these tube walls also, right? So we need to include these three quantities when we are calculating the overall heat transfer coefficient. So on the outer surface, this is 1 by Hi into Ai. Let me multiply and divide by A0 in the numerator and denominator so that I can cancel A0 at the end. Okay, plus at this is at the inlet. Then we have the tube walls. For the tube walls, the expression is, we know it is a expression for resistance is log of R2 by R1 or RO by Ri in this case by 2 pi Lk, where K is the thermal conductivity of this brass tube and L is the total length of this tube. Here also let me multiply and divide it by A0 so that I can cancel A0 from LHS and RHS. After that, we have the outside surface area, for which the thermal resistance is given by 1 by H naught A naught. Here there is no need to multiply and divide by A naught. A naught is already present here. Okay, is this expression clear? So I hope it is clear. So let me divide, cancel A naught throughout this. So it can be rewritten as 1 by Hi into A naught by Ai. A naught by Ai would be, what would be the difference in two cases? A naught is actually 2 pi Rho into the total length, and Ai is 2 pi Ri into the total length. So it would be just a ratio of Rho by Ri plus ln Rho by Ri. This A naught will get cancelled. Let me cancel this A naught here. Okay, and A naught by 2 pi Lk, that is 2 pi R naught L by 2 pi Lk. 2 pi will get cancelled, L and L will get cancelled, so it would be just R naught by K, not R naught, R outer by K, and this is just 1 by Ho. Is this expression clear? Let me know if the first expression and the second expression are clear. Take a minute to go through it. Understand that the first term here is the thermal resistance associated with the inner side of the tube. The second term here is the thermal resistance associated with the tube wall, and the third term here is the thermal resistance associated with the outside of the tube, conductive with corresponding conductive heat transfer coefficients Ho. Okay, now this U naught is what we have to find out, the overall heat transfer coefficient. Now let's see, what all do we know in these expressions? Hi is not given to us. Heat transfer coefficient at the inlet is not given to us. Radius of outer and inner surfaces, inner tubes are given to us. Inner and outer diameters are 13.4 and 15.9. So this is 15.9 by 2 mm, and radius of inner is 13.4 by 2 mm. Okay, so this quantity is known to us. Rho and Ra is known to us. K is for which material? We have K for the fluid here, and we have K for brass here. Do we have any other K? No. Which of these is this K representing? Is this K for water or K for brass? It would be K for brass, because this term denotes the thermal resistance of this brass tube. So the corresponding K value is 114 watts per meter Kelvin. 114 watts per meter Kelvin. And Ho is known to us. I think Ho is given to us. Ho is given to us to be the heat transfer coefficient for condensation on the outer surface of the tubes is 13,500 watts per meter square Kelvin. So this is 13,500 watts per meter square Kelvin. So all these quantities are known to us. It means that if we find out this HI, we can calculate this overall heat transfer coefficient. So now the problem reduces to finding out HI. How can we find out HI? Okay, if we go back to the problem, HI is associated with the tube water interface heat transfer coefficient, convective heat transfer coefficient, and we have been given the density, Cp, kinematic viscosity, the Prandtl number, all those properties for this water, and also the velocity of this water also is given to us. So we could in practice use the Nusselt number correlations to find out this unknown heat transfer coefficient. So for that we need to know what kind of flow regime is this for this water flow through the inside of the tube. And how do we find that? We need to find out the Reynolds number, right? So let's calculate the Reynolds number based on diameter for the water that is flowing through the inner tube. If we know the density and velocity, what would be the expression for Reynolds number? It would be density into mean velocity into diameter at the inlet divided by kinematic viscosity, right? We know all these expressions that is given in question. Let's substitute them and find out the Reynolds number value. Density is 995.025, 995.025 multiplied by what would be the velocity. Velocity is given to be 1.25 meters per second. And what is the diameter? Diameter is 13.4 millimeters. We'll convert that to meters by dividing by 1000. Whole divided by the kinematic viscosity. Kinematic viscosity of water is given to be 769 into 10 power minus 6 Newton seconds per meter square. 769 into 10 power minus 6 Newton seconds per meter square. Let me confirm the value. Yes. So if we evaluate, we will get the Reynolds number corresponding to the water flow through the inner tubes. Let us calculate that value. Let me quickly substitute them and calculate it. 995.025 multiplied by 1.25 multiplied by 13.4 divided by 769 into 10. 21673. What is the units for Reynolds number? Reynolds number doesn't have any units, right? It is a dimensionless parameter. Okay, it's a dimensionless number. So for flow through tubes, if we get Reynolds number that is greater than 2300, 2500, we can say that it is in a turbulent regime, right? So for such cases, what do we do? Once we identify the type of flow, we go for Nusselt number correlations, right, to get the heat transfer coefficient. Usually we should go and look at the tables, non-empirical correlation tables, to get the Nusselt number correlation for turbulent flow inside a tube for given Reynolds and Prandtl numbers. But in this case, let me give the Nusselt number correlation directly. The Nusselt number correlation that we have to use in this case is Reynolds number to the power 0.8 and Prandtl number of the fluid to the power 0.4. This is the expression that we have to use for turbulent flow through a tube surface in which the fluid is getting fluid is getting heated up, cooled down. The fluid is getting heated up or cooled down in this case. It's a cooling water, so it will get heated up. Yeah. That is why the factor 0.4 is here. If it was a heating of the fluid, this factor would be 0.3. Can someone evaluate, okay, what is the value of this Prandtl number for the fluid? Prandtl number for the fluid is 5.2. Can someone evaluate the Nusselt number? Let me calculate the Nusselt number. 0.023 into Reynolds number to the power 0.8. 21673 power 0.8 multiplied by Prandtl number to the power 0.4, right? It is 5.2 power 0.4. So we are getting a value of 130.88. So Nusselt number is 130.88. Now from this Nusselt number we have to calculate. Remember, why did we calculate this Nusselt number? If we go back to the expression, here this was the expression that we wrote for overall heat transfer coefficient, and in that expression only the convective heat transfer coefficient for the inner tube was the unknown. To find out this HI is why we use the went for this Nusselt number calculation. This Nusselt number we can rewrite it as HD by K, right? Nusselt number equal to heat transfer coefficient at the inlet into diameter at the inlet divided by thermal conductivity of the fluid. That is 130.88 equal to HI is unknown in this case into diameter of inlet 13.4 divided by thermal conductivity of the fluid. What is the thermal conductivity of the fluid? It might be given in the question. Thermal conductivity of the fluid water is 0.620 watts per meter. Watts per meter Kelvin. There should be a Kelvin here. .62. So let's try to evaluate this expression. 130.88 multiplied by 620 divided by 13.4, 6055 is the 6055.64 is the value of HI that I am getting. HI equal to 6055.6 watts per meter square Kelvin. Okay, all this exercise was to find out the HI value which we could substitute in this overall heat transfer coefficient expression to get the value for overall heat transfer coefficient. So I think we have time. Let's quickly substitute that and find out the value of overall heat transfer coefficient. 1 by U naught equal to 1 by HI into RO by RI. 1 by 6055.6 into radius of outer by radius of inner, that is equal to diameter of outer by diameter of inner, that is 15.9 by 13.4 plus log of R outer by R inner into R outer by K. R outer by K. K is thermal conductivity of brass. Remember, 114. Plus 1 by HO, that is 1 by 13,500. Okay, this is the expression that we have. If we evaluate this, we will get the value of U naught. If someone wants, they can substitute and solve it now. We'll take, yeah, we have time. Let me substitute this and find out the value. You can solve this along with me. 15.9 divided by 13.4 multiplied by 6055.6 plus ln of 15.9 divided by 13.4 multiplied by 15.9 divided by 2 into 114 plus 1 divided by 13,500 Did someone get the answer? One by 6,000. 1 by 13,500, 15.9 by 30.4. Yeah, I think if we evaluate that, you should get some value around 3,500 46.72 watts per meter square Kelvin. Okay, is that correct? Okay, this 15.9 should be converted to meters, so you should multiply by 1000 in the denominator. Take a minute to go through the problem and solution, and if there is no other queries, we will move on to the next problem for today. the answer that I have in my answer book. You can check this answer. I'm not sure if it is correct or not. You can substitute these values and check this answer. Okay. Okay. With that, let me move on to the next problem for today. That is problem 4. Let me read out the problem statement. Saturated steam at 0.14 bar is condensed. Okay, this is the same problem statement. Let me rephrase what is different in this. I will read the problem statement first. Saturated steam at 0.14 bar is condensed in a shell and tube heat exchanger with one shell pass and two tube passes consisting of 130 brass tubes, each with a length per pass of 2 meters, same as before. The tubes have inner and outer diameters of 13.4 millimeters and 15.9 millimeters respectively. Cooling water enters the tubes at 20 degrees Celsius with a mean velocity of 1.25 meters per second. The heat, it is same as before. The heat transfer coefficient for condensation on the outer surface of the tubes is 13,500 watts per meter square Kelvin. It is again given to us. And the overall heat transfer coefficient of the system is also given to us. Assume this to be U0 with respect to the outside surface area. Now we have to determine the steam condensation rate. Condensation rate of the steam, which is the hot fluid in this case. Take a minute to go through the problem, and after that we will solve this. Okay, this problem statement, the first paragraph is same as before, except that here last time we were trying to find out this U0, and here U0 is given to us, and we have to find, on top of that we have to determine the steam condensation rate. Remember that it is the steam that is condensing in the shell side, and on the tube side it is the cooling water that is flowing. And we have been given one more expression for effectiveness. The effectiveness NTU correlation is given to us, which is given by effectiveness equal to 1 minus exponential of minus NTU, which is number of transfer units. So what we need to find out is mass flow rate or the steam condensation rate, that is same as the mass flow rate of the hot fluid, because it is the steam. This is what we have to find out. We can express the total heat that is carried by the steam, because since it is condensing, we can express it as the mass flow rate times the latent heat of condensation, right? And from this we can write the unknown mass flow rate of steam equal to the total heat transfer rate divided by latent heat. Is that okay? Okay, now in this expression we know the latent heat of steam, that is given to us as 2373 kilojoules per kilogram. But we still don't know this Q, but we have been given an expression for effectiveness, right? So what we can do is we can write this Q in terms of effectiveness. What is Q? Q is effectiveness times Q max, right? Where Q max is the maximum possible heat transfer rate. Now let's write an expression for Q max. Q max equal to C min into temperature of the hot fluid at the inlet minus temperature of cold fluid at the inlet, right? Now what is this C min? That is the minimum heat capacity of either the hot fluid or cold fluid. But in this case we can see that the minimum heat capacity, that is C min, will correspond to water, because the steam is undergoing a phase change, and so the heat capacity associated with phase change is large. So the C min will be associated with water because it is the heat that is carried by the water to change its temperature through unit temperature, unit degree Celsius or Kelvin. Okay, so C min is associated with water, so we can rewrite C min as mass flow rate of water into C of water. Here instead of water I am writing cold fluid into temperature of inlet, hot inlet, minus temperature of cold inlet. Okay, now what all do we know from these expressions? Temperature of the hot fluid at the inlet, it is the steam, right? So it is 327 Kelvin, it is given to us. And temperature of cold fluid at the inlet is also given to us. Where is it? 20 degrees Celsius. That is 293 Kelvin. So C of water, is it given to us? Yes, it is given to us, 4178 joules per kilogram Kelvin. C of the cold fluid, that is water, is given to us as 4178 joules per kilogram Kelvin. Now if we know the mass flow rate of the cold fluid, we can find out Q max. Now look at the problem and see how we can find out the mass flow rate of cold fluid. The cold fluid is flowing through tubes, 2 pass tubes, and there are 130 such tubes, and the mean velocity of cold water in each of these tubes is known to us. So mass flow rate we can write as the density of water into cross-sectional area into the velocity, mean velocity. This will give us the mass flow rate per tube, and there are 130 such tubes. Right? So if we evaluate that expression, we will get the mass flow rate of cold fluid. So let's calculate that. Density of water 995.025 multiplied by area of cross section would be where is the area of cross section? Okay, yeah, 13.4 millimeters. millimeters multiplied by the velocity is 1.25. Area of cross section is pi r square, pi d square by 4. So this would be pi d square by 4. So I'm getting a value of 22.8 kilogram per second. Okay, was that clear? So if I substitute for that all those values, we will get Q max as 22.8 multiplied by 4178 multiplied by 327 minus 293. .8 multiplied by 4178 multiplied by 327 minus 293. So we will get Q max to be 3238.785 kilowatts. Okay, now if we know the effectiveness, we can calculate the required Q. So the effectiveness is given by 1 minus exponential of minus NTU. Effectiveness is given by 1 minus exponential of minus NTU. Now what is this NTU? The expression for NTU, we know that it is UA divided by C minimum. So UA we have been given U naught, so we can write it as U naught into A naught. UO means the overall heat transfer coefficient of the outer surface of the tube and outer area of the tube divided by C min. C min is mass flow rate of the cold fluid into C of the cold fluid, which is equal to, let us calculate this value. U naught is 1837.59 area of the outer surface would be pi d into length per pass is 2 and it is a 2 pass, so it will be 4, and there are 130 such tubes, divided by mass flow rate of cold fluid is 20.8 kilograms per second into C of cold fluid is 4178 joules per kilogram Kelvin. Okay, let's evaluate this expression. One 837.559 multiplied by pi d square, no, not pi d square, pi d into 4 into 130, that is the total number of tubes and passes, divided by 22.8 into 4178,000. So if you evaluate, we will get an NTU value of 0.5, and if we substitute this in effectiveness, we will get 1 minus e power minus 0.5 equal to 1 minus e power minus 0.5 equal to 0.39. We will get an effectiveness of 0.39. Okay, is that part clear? Substituting for this effectiveness and Q max, we will get the value of Q. So Q would be effectiveness times Q max, which is equal to 0.39 into 3238.7856. 3238.7856, which is equal to 3238.7856 into 0.39, 1263. Kilowatts. Okay, now let's go back to our initial expressions. Oh, sorry. Something happened. Let me wait for the program to respond, otherwise whatever the ink markings that I have written will be lost. By that time, let me know if there was some confusion till this point. Let me wait for the program to respond. By that time, recollect whatever we did till now for this problem 4, and let me know if there was something that was not clear. So by that time, the program from my end is not responding. By that time, can you calculate the value of mass flow rate of the hot fluid, which is the condensation rate, that is equal to Q divided by HFG, Q divided by Q divided by the latent heat of vaporization. Let me disconnect and connect. Let me know once you have the solution for that. Give me a moment to sort out this issue. By that time, can you please calculate the final result? The final result, the mass flow rate of hot fluid will be this Q by HFG, that is 1263.12 divided by, what was HFG? 1263.12 divided by 2373. Let me do that. 1263.12 divided by 2373. So the answer is 0.53 kilograms per second. That is the mass flow rate, required mass flow rate, not the required mass flow rate, that is the condensation rate that we will achieve through this shell and tube heat exchanger. I think I will have to close this program, but if I close I will lose all the ink markings. okay. Let me restart from here. I think you are not able to see my screen, right? Give me a moment while I go for screen. Okay. The mass flow rate of hot fluid was Q by HFG, which was what was the value that I said? 1263.12 divided by 2373. So we will get mass flow rate of hot fluid or the condensation rate as 0.53 kilograms per second. This is the final answer for this problem. Take a minute to go through whatever we discussed. I'm sorry I don't have the previously written bugs because my PowerPoint got crashed and I lost whatever I wrote earlier. But yeah, you can take some time to go through whatever we discussed. Take 2 minutes to revise what we did to solve this problem. After that, we will move on to the last problem for today.
Hello, sir.
Yeah, hello.
Sir, that TC naught, it was given 44 degrees centigrade.
Which one is 44 degrees centigrade? Yes,
TC naught.
TCO, yes.
But our TC equal to 305 Kelvin.
TC equal to 305 Kelvin.
How it would be 305? It will be 309, 312, 390 now, right?
Give me a moment.
317. 317.
317. Yes. Okay. That TC is actually the average of
Average temperature.
outlet and inlet.
Okay.
Okay. So outlet is 20 and inlet is 40. It should be the average of outlet and inlet. That is what I think.
That means 20 plus 44, 64 by 2, 32 plus 273. Am I right? 32 plus 273.
Yes. Let me calculate.
Yes, sir. 32 plus 273, 305.
Is it coming correct?
Yes, sir.
Okay. Yeah. Because it showed that TC value because whatever the properties that we are showing, that is this density, Cp, kinematic viscosity, and this thermal conductivity, all these properties have to be evaluated at the average
Mean film
temperature.
temperature. Mean film temperature. Yes, sir.
Yes, yes, not the.
Bulk mean temperature.
Yes, yes, right. So shall I move on to the last problem for today?
Sir, what is this brass 70 by 30, sir?
Which one? Oh, brass.
For
Brass.
70 by 30.
Brass 70 by 30.
What is that?
I'm not sure actually. I think that should be some grade of brass, but at this moment I don't know what that represents. Brass has some grades, right? It is a
Grade,
combination of.
grade. Maybe brass grade.
Yes, yes. It is a combination of uh, different metals, right? So maybe that combination ratio is that what it represents, but I'm not sure. It is some grade that
Okay,
is
composition.
representing the
Maybe
brass
brass
that we are.
composition, maybe.
Huh? Yes, yes. It
Okay.
it could be, yes. Yeah, I didn't notice that. Thank you for pointing that out.
Okay, sir.
Okay. So shall we move on to last problem? Yes. Okay, this is the last problem for today, problem 5. Let me read out the problem statement. A fin tube cross flow heat exchanger. There is a cross flow heat exchanger. Fin tube. Okay, there is a cross flow heat exchanger, which is used to use the exhaust of a gas turbine to heat pressurized water. Okay. Exhaust of a there will be a cross flow heat exchanger. This is the inside and this is the outside cross flow. Okay. The exhaust of a gas turbine is used to heat pressurized water. Now, laboratory measurements are performed on a prototype version of the heat exchanger, which has surface area of 10 meters square. Surface area is 10 meters square. To determine the overall heat transfer coefficient as a function of operating conditions. Measurements made under particular conditions for which mass flow rate of hot fluid is equal to 2 kilograms per second and mass flow rate of cold fluid equal to 0.5 kilograms per second, and inlet temperature of hot fluid is 325 degrees Celsius and inlet temperature of cold fluid is 25 degrees Celsius. For these conditions, the measurements reveal a water outlet temperature of 150 degrees Celsius. Say if this is water, the inlet temperature of water is 25 degrees Celsius and outlet temperature of water is 150 degrees Celsius, and inlet temperature of the hot gas is 325 degrees Celsius and outlet temperature is not given to us. Okay, now we have to find out the overall heat transfer coefficient of the heat exchanger. Overall heat transfer coefficient is what we have to find out. The properties of water and air is given to us, and the effectiveness NTU correlation for the given configuration is also given to us. In this CR is the ratio of minimum heat capacity to the maximum heat capacity among these two fluids. Take a minute to go through the problem, and after that we will discuss the solution. there is a hot flow heat exchanger with the water that is getting heated by using a hot exhaust gas as a cross flow. Oh, this is not counter flow, this is cross flow. Sorry. Water is coming in at it is same, right? $25. Have you gone through the problem statement? Yes. So let's try to solve this problem. First, we have been given an expression for effectiveness, right? So let's try to evaluate this effectiveness first. Because what do we need to find out? We need to find out the overall heat transfer coefficient. So overall heat transfer coefficient we can express in terms of number of transfer units, right? Overall heat transfer coefficient U equal to C minimum into number of transfer NTU divided by area. This is expression for overall heat transfer coefficient. In this, A we know, I think it is given to be 10 meters square, and if we find NTU and C min, we can calculate this overall heat transfer coefficient. For finding out this NTU only, that effectiveness expression was given. So let's first try to get what is the C for this hot fluid and C for the cold fluid R. So C is short for mass flow rate into Cp for cold fluid is equal to it is 0.5 multiplied by cold fluid for us is water, right? 4203. Which is equal to 4203 by 2. 1.5 units would be watts per Kelvin. Similarly, the heat capacity capital C for hot fluid will be mass flow rate of hot fluid into Cp for the hot fluid, that is 2 kilograms per second multiplied by hot fluid is the air, for which Cp is 1040 joules per kilogram Kelvin. So this is equal to 2080 watts per Kelvin. So we can see that they are very close values, but still C hot is lesser than C cold. So we can say C hot is the C minimum among these, and that is the C min value. Okay. Now in the effectiveness expression, we see a CR value, that is the ratio of this specific heat, which is given by C min by C max. So CR equal to 2080 divided by 2101.5. If we evaluate that, we will get 2080 divided by 2101.5, we'll get 0.989. That's close to 0.99. That is the CR value. Okay. Now in this effectiveness expression, there is an effectiveness, there is a CR, and there is NTU. NTU would be unknown at this point. CR we just now calculated, and effectiveness also we can calculate. What is effectiveness? Effectiveness is Q by Q max, right? And for which fluid we can calculate this Q? Because for the cold fluid, both inlet and outlet temperatures are known, right? So we can calculate Q for cold fluid. That is C of cold fluid into temperature of cold fluid at the outlet minus temperature of cold fluid at the inlet. And Q max, the definition for Q max is, it is C minimum into temperature of hot fluid at the inlet minus temperature of cold fluid at the inlet. Let's try to substitute these values. (150 minus 25). C minimum, that is 2080 into hot inlet minus cold inlet, 325 minus 25. Okay, so let's see what is the effectiveness. To 101.5 multiplied by 125 divided by 2080 divided by 300 is 0.42. This is the effectiveness value that we are getting. So effectiveness is 0.42 and CR is 0.99. So if you substitute for these two values in this expression, we can calculate the, because effectiveness is known 0.42 and CR is known 0.99. The only other unknown is NTU, and if you substitute these values in this expression, we can calculate the value for NTU. So let me write down the NTU value directly. NTU can be calculated by substituting effectiveness, CR in effectiveness NTU correlation. And let me write down the value that we will get once we substitute this in that expression. The NTU value that we should get is 0.8125. Okay. Now remember that we said what we wanted to calculate was overall heat transfer coefficient, and overall heat transfer coefficient we can express in terms of NTU, as it is C min into NTU by surface area available for heat transfer, which is again C min is 2080 into NTU is 0.8125 divided by area available for heat transfer is given to be 10 meters square. So the overall heat transfer coefficient would be 2080 multiplied by 0.8125 divided by 10, 169 with units of watts per meter square Kelvin. Okay, that was the solution to our problem. Take some time to go through
Sir?
Yeah.
Sir, can we get that NTU value very easily? It seems to be very lengthy, complicated equation. Is it required trial and error method or something else? Can we get simplified equation for NTU here?
That's what I'm looking at. Let me see if I can solve it with simple calculations. We might need to make use of some computational techniques to solve this. Let's see. We can't solve this simply. We need to make use of some computational numerical techniques. Yes, right. Because the unknowns has different powers, NTU power 0.22 and NTU power 0.78, which would be difficult to solve simply. Yes, you are right. Epsilon 1 minus epsilon. No.
It have both inside and outside also exponential terms.
Yes, right.
So I think it won't be solved easily.
Yeah. It won't be a simple equation to solve. We would have to rely on some computational techniques or numerical techniques.
So definitely in the exams it won't be asked like that, right?
No, this won't be asked. Maybe
he may give, if he asks that, he has to give the NTU value.
Yes. Maybe some simple expression for epsilon NTU like this expression. Some expression which you can solve will be given.
Okay. Yeah. Sir, is it the last session we are meeting?
This is the last session for last problem solving session, but I think there will be one more 1 hour session which would be like a summary session for the complete topics. So it would be a 1 hour summary session. That would be there, but I don't know when it will happen. I have to check with the NPTEL team.
Actually, I was very much impressed with the way you are explaining the problem, sir.
Oh, but today's session, actually I was not satisfied with today's session.
No, these are all direct problems only, sir.
Yes. Yeah, but apart from that, previous sessions I really enjoyed. And you were attending continuously. I think from first few sessions you were not there, but after that you were continuously attending the sessions.
Yes, sir.
Yes, right. So it is a motivation for me. Like in most of the classes, I think you are the only one attending this session, right?
Yes, sir.
So it's a motivation for me to prepare and come also. If no one is attending, then I would be just simply explaining. When you are attending, you will be asking me questions, and I will think more about that problem. So it will help me also to understand the problem better. So it's not only me, it's you also that is making this session better.
You are belongs to which state, sir?
Which
State.
Okay,
state?
I'm from Kerala.
Kerala. Oh, Kerala.
Yes.
Actually, I have studied at Kerala, sir, NIT Calicut,
Oh, okay, okay, nice. You studied in NIT Calicut. Okay, okay.
in the year 92.
92. Oh, nice. Long back. Nice, nice. So, where are you from? Uh,
Andhra Pradesh.
Andhra Pradesh. Okay, okay. And right now you are in Andhra Pradesh only, or
Yes, sir. I am
okay,
working as a faculty.
okay, okay, nice. In a college in Andhra Pradesh.
Yes, sir. Yes, sir.
Nice. And are you teaching this e-transfer subject?
Yes, sir. Yes, sir.
Okay, okay, nice. So, when would be the exam for this subject?
28th or 27th, maybe. I am writing parallelly both. Applied thermodynamics and this also.
Okay, 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 okay. So, how was the tutor? Not the problem solving sessions. How was the lectures from professor?
Actually, I have not gone through the lectures, sir, till now. I didn't get the opportunity.
Okay. Anyway,
Time is
you
not
already know
permitting.
the subject, so yeah,
Hmm.
it would still be okay. Yeah.
I heard one or two lectures of him, but
Okay.
none
Okay.
of the lectures have not gone. I need to go
Okay. Okay. Yeah.
before the exam. Before the exam, I need to go.
Okay. Actually, the lectures are really good.
Yes, yes, definitely it would have been, definitely.
Yeah. Yeah. Yeah.
I agree that.
Okay. So yes, as I said, the problem solving sessions are over. I had conducted, I think, 12 sessions for the 12 weeks, plus one extra session yesterday that you attended. Yes. And apart from that, there would be
Yes, sir.
one more session which would be like a 1 hour summary session. uh, I don't know on which date it would happen, but yeah, that would be, I think, communicated via email. Is that clear?
Sure, sir. Definitely. I will attend.
Yeah. So if there is nothing else, I think we will close the session here.
Now I think you are pursuing PhD at IIT.
Yes, yes. Actually, I'm a PhD student at IIT Bombay. Yes, right.
Are you pursuing a PhD at IIT, sir?
Yes, yes. I'm. Is my voice clear? Hello. Hello.
Hello, sir.
Yeah. Yes, I am pursuing PhD at IIT Bombay right now. Yes.
IIT Bombay. Okay, okay.
Yes, yes.
You are in the project research.
My project is related to atomistic simulation, phonon mediated thermal transport. It is thermal energy transport, but studying thermal energy transport at the atomistic scale.
Atomic.
Atomistic scale, like thermal transport through lattice vibrations,
Okay, okay.
studying on that computationally. That is
So
my
it's so
domain.
complicated. I think it's so depth.
It's a good like niche area, yes, but it's good.
Okay.
Yeah. So what would be your area of expertise? Like
Wish you all the best, sir.
which one?
Wish you all the best, sir.
Wish me. Okay. Uh, thank you. Thank you. I was asking, what is your area of expertise?
It's I have done my PhD at gas turbine blade cooling techniques.
Okay, it's mostly fluid.
Gas turbine blade cooling techniques
Okay, okay, okay. Nice,
at
nice.
Andhra University.
Okay, okay. Nice. So, yeah. I think, yeah, we will meet again for the summary session.
Anyway, nice meeting you and nice talking with you. And I will be in touch with you, sir. Definitely.
Yeah, yeah. You have my contact, right? We will be in
Yes, sir.
touch.
Yes, sir. Yes,
Yeah.
sir.
Okay.
Thank you very much for all your patience lecturing
uh,
throughout the
uh,
journey.
please don't call me sir. It's you can call me by my name, Nidish. Okay.
Okay. Good night, sir. Thank you very much.
Okay. Thank you. So we will meet again.
Okay. Sure.
Okay. Thank you. Bye. Shall I
Bye.
close the session?
Yes, sir.
Okay. Good night. Bye.